Now the question is, what is so special about nanoscale? Okay, so since the particles are small, therefore few atoms are present, and that translates to a high surface to volume ratio. The high surface area causes the particle to act and react differently with compared to its bulk form. Another reason why nanoscale is unique is because it is on the scale of small biological structures such as protein and DNA and whatnot. This enables many medical researchers to design tools, treatment and therapies that are more precise and personalized than the conventional ones. It is also where the quantum mechanics meet classical mechanics, or the peculiar realms of quantum world meet the physical law of our world. So the image on the right shows the simulation of confined electron motion in a nanowire. So in this case, the quantum property is more dominant than the classical law that we have in our world. Another example is the phenomenon of quantum tunneling effect, which made possible the scanning tunneling microscope and flash memory for computing. And all these are the reasons we have many new interesting properties or phenomena that are not present in the bulk form, such as opaque substance become transparent. Okay, inert material can become catalyst in the nano form. Stable material can turn combustible. Solid can turn into liquid at room temperature, and insulator can become conductor. The picture in the bottom shows various metal nanoparticles in colloidal forms. If we compare the color in terms of the optical properties of the colloids compared to its original bulk material, it is totally different. For example, gold in this case is red in color as compared to the color of gold that we are used to. And silver will become yellow, aluminum will become white, copper will become slightly dark greenish, and brass alloy nanoparticle will become more like chocolate in color. These are the new optical properties of several metals when they are in nano forms due to its small in size. To be able to imagine the scale of nano or the word of nano, we need to get back to our prefixes with the help of this diagram. So a meter is roughly 3.3 feet, which is our feet, and it is equal to 1 billion of nanometer. As to the larger scale, we have kilometer, we have megameter, we have gigameter, and so on and so forth. But we want to go to smaller scale, which begins with the macro world, which is now more than 1 million of nanometer. So if you can imagine, in this macro world, it is roughly the size of a letter in your TV remote, the size of an ant, the aperture in your smartphone camera, a spider silk, and this is a bristle on the tip of a finger lady or okra. And it is also within the size of various electronic components such as diode, capacitor, and etc. So most of the objects here in this world, in this scale, are still visible with naked eye. But if we go smaller, we will enter the micro world. For micro world, the size is around 1,000 to 100,000 of nanometer, which the word that bacteria and viruses lives in. So this is something which is well recognized these days, which is a coronavirus. We have also the lab on chip, which has been used a lot in DNA testing, for example. This is a single crystal of ice. What else? This is our red blood cells, and this is micro electromechanical system or devices, or in short MEMS. So these objects are all within the micro scale, and this structure or these objects still can be resolved by using light, so therefore can be viewed under the optical microscope. Then when we start to get smaller, around 1 to 100 nanometer, we actually have entered the word nano or nano world, where light can no longer resolve any object in this world. Few examples here. First, we have a protein structure, which cannot be seen under optical microscope. If you want to view the object in this nano world, we require an electron microscope, some of which can magnify the image of the object up to 1 million times. The image on the left shows the carbon atoms which form synthetic diamond, and of course as viewed from an electron microscope. So on its right, if you can see from here, we have a particle of silver, nanoparticle of silver. This picture is quite interesting actually. We are going to talk more about this picture in the next section. This is the image of a transparent region of a butterfly wings, which exhibit anti-reflection behavior caused by these small nano pillars covering the region. The picture on its right shows the superparamagnetic iron oxide nanoparticles, which carries big potential, especially in the bioimaging application. And finally, the picture on the bottom left shows a molecular person, or we call it stickman, right? Consisting of 14 carbon monoxide molecules arranged on a metal surface and imaged by a scanning tunneling microscope. So now, if you haven't noticed, these objects can easily be classified into two categories. In the left side, we have things man-made, and on the right, we have things natural, which we will discuss these two categories in details in the next section. To be able to imagine the nano world or the smallness of nanoscale, let's take this analogy. If a nanoparticle is the size of a football, so a virus will be the size of a person, and a red blood cell will be the size of a football field. A small donut will be roughly the size of Malaysia, the land area of Malaysia, and a turkey will be the size of the earth. So that is the comparison in the size of a nanoparticle compared to our everyday objects, so that we can appreciate the scale of nano world. So that's all for this topic. In the next section, we will discuss about the natural and man-made nanomaterials. Thank you.